Welcome everyone. My name is Frank Smith. I'm the CTO and co-founder of Pilot Photonix. We're a 20-person startup based in Dublin, Ireland. Today I'm going to talk about our Astro frequency generator, which leverages the photonic domain to outperform electronic frequency generators, and in doing so enable the next generation of space communication, observation and science. Okay, so as we push the limits of global connectivity, of Earth observation and of space science, there's a continuous need to drive to higher bandwidths, higher data rates, more precise measurements and greater resolutions. In order to do this, we need to move away from the microwave frequency domain that everyone is used to and comfortable with, and move to higher frequency bands such as the millimeter wave bands and the sub-terahertz bands. However, doing so in using traditional electronic methods faces very steep hurdles. So these technologies today have very limited bandwidth. They suffer from noise issues, very high power dissipation, and obviously the size and weight. They use kind of big, bulky hardware. So our breakthrough is to generate these signals in the optical domain rather than in the electronic domain. The optical domain frequencies start at around 10,000 times higher than the electrical domain, than the gigahertz rates that we use in the electrical domain. And so you're starting from a much higher resolution, and you can drill that down and make very accurate, very stable frequency sources working from the optical domain. We use optical frequency combs, which are a Nobel Prize winning technology. We combine them with state-of-the-art photonic integration technology and also advanced semiconductor packaging. And we combine these together to make a system which offers clean, stable signals at a fraction of the size, weight and power of today's technologies. You can see the type of multiplier chains that are used today to generate these very high millimeter wave and sub-terahertz signals in the top. And then Pilot's chip, which is shown alongside, it's a fraction of a size of a €1 coin there in the bottom right. So that's our chip there that generates this. So how does it work? Well, comb lasers are known to bridge the microwave and the optical worlds. So effectively what you get with a comb laser is multiple optical frequencies that are precisely spaced by microwave frequencies. And so you can use those to generate the frequencies at many different bands. So how does it work? We integrate all of these functions onto a photonic integrated circuit, which is made in indium phosphide, a material that has been proven in space very widely. So we apply a low frequency RF signal on the left-hand side. We have a patented technique which generates the optical comb. It's called gain switching, and this turns it from a single wavelength into many, many wavelengths separated by the RF frequency you apply. We can then pick any two lines from that comb and mix them together on a photodetector, and this creates our millimeter wave or our sub-terahertz wave. So we can do anything from, say, 4 gigahertz all the way up to 240 gigahertz from a single part. In terms of the advantages and competitive edge of this technology, the main one is its ultra-wide frequency range. So a single agile source can be used for all of these frequency bands. That not only simplifies the system architecture for satellite and spacecraft designers, but also simplifies the qualification process. Now, rather than having to qualify separate parts for each of these bands, you just have to qualify a single part, and that hugely improves supply chain as well. In terms of performance, size, weight and power, we have excellent frequency stability, phase noise, and the source itself has dramatically reduced size, weight and power versus the electronic techniques. But furthermore, now that we're in the optical domain, we can actually transmit over much longer distances than you can with copper cable and harnesses. An optical fiber is a low loss electromagnetic interference tolerant medium, which requires much less power to drive, so further size, weight and power reductions there. Overall, it's a really future-proof platform suitable not just for today's missions, but also emerging standards and missions. Oh, sorry, that should have animated. Apologies, yeah. And so just to key takeaways then. So today's and advanced next generation space applications demand that we move from microwave to millimeter wave frequencies and even beyond to sub-terahertz frequencies. This will allow both space communication, Earth observation, and space science applications to advance. But electronic methods face severe limitations, as I mentioned: noise, bandwidth, size, weight, and power issues. Our Astro FG innovation, Astro frequency generator platform, it leverages the optical domain, and in doing so overcomes these challenges in the electronic domain. We deliver microwave all the way up to millimeter wave and sub-terahertz bands from a single source with high performance and low size, weight, and power. And really at this stage, we're seeking to partner with integrators to design in this technology into their next generation space payloads. So let's deliver the future together. Thank you very much.